Hi, my name's Dan, and this video is one of a series of videos, a short series of videos I'm doing about simple bistable memory circuits in digital electronics, which is part of a larger suite of videos that I'm doing, where I go from the fundamentals of logic gates, and back even before then, I've got some videos about logic circuits and about not binary, Boolean algebra, Boolean rules, and I'm working my way through to from these principles to a 4-bit simple CPU that's simulated. So there's a roadmap of where I'm going on this wider context in the description below. There is also a link to this software that I'm using, which is DigitalWorks, which is uh, a simulation of digital electronics, and it's more visual than the real thing, and also it's cheaper because I don't need to buy parts. And it's quite satisfying to create this simulated CPU in this software. Um, so please do create along with me. So that's kind of the wider context of what I'm doing. And right now in this video, we're looking at the video series is short series is about memory circuits, and we've done simple bistables. We've done a flip flop. We've done before that a latch. And I finished off the last video by talking about the fact that the SR flip-flop, which is where we'd got up to, has a small problem, which is that if we set both the S and the R inputs to high and then hit enable, once we let go of enable, as in let the enable line go 0, the output is not determined by the circuit. It's determined by either the vagaries of electronics, if we're doing it in electronics, or by the order of simulation, which is the case that we've got here, the simulation. We cannot guarantee what's going on in that situation. But the question is, why would we actually ever want to have both S and R at the same time? So what we're going to do is we're going to take our SR flip-flop, which we had last time, and we're going to adapt it so that we don't have this problem. And in fact, we're going to change it so that instead of having an S input and an R input, we're going to have one input, and we're going to call it a D input for data. And if it's high, it's going to be equivalent to using the S. So it's going to set our output qubit when the enable is used. And if it's low, it's going to be equivalent to reset. So again, when enable is hit, that's going to set our output to low. And thinking about this is actually really, really easy to achieve, because all we need to do is to have one wire that's coming in and make it go into reset when it's low. So when it's low at the input side of that NOT gate, then it'll be high at the R input to the SR flip-flop. And we don't use the NOT gate if we're going into the S, and we can turn this into a single input. And in fact, I'm going to use tags. I'm going to go straight to creating a macro for this because it's such a simple adaptation. Where's the wire? There we go. I'm going to just add tags on for the other things, which is the enable and the Q and the not Q. Q and not Q. So we'll turn it into a macro first, and then I will just create a testing circuit to demonstrate that it's working. So the only addition is this NOT gate in this case, but we're going to change this. We'll put an annotation in here just to say this is a D input. Okay. Just moving that a bit closer. Okay, so that's the circuit. Let's do the templates, which is the visual thing that we'll see. So the first thing I'm going to do is I'm going to change the name, because if I forget, then that gets annoying. We don't need 2 inputs. We're just going to have 1. And we're going to rename it to be D, which is our data. And we're going to have, shall I move enable round to the sides? Why not? I think it might be worth it. Maybe it should have been at the side already with the SR, but hey, these things, sometimes these things are a bit arbitrary. It feels more kind of symmetrical if I do it like this. And sometimes how it feels and how it looks can be important to me. Let's just move that whole thing up a little bit. There we go. Right, so we need to do the wiring up to connect these things together. We're in the right set of things. Yes, so in the template I need to change where it says R. I forgot, but I can do that whilst I've got it open here for doing the connection of the tags to the pins. So that's now D. That's the enable. Come on. There's a very small movement to the mouse, and my mouse pad's a bit sticky, so I found it hard to do it quite that closely. Q, not Q. There we go. So let's save that. And this is now no longer an SR flip-flop, it's a D flip-flop. And then let's have a new circuit to test it. Circuit has changed, so current circuit, yes, okay, I suppose we better just in case. Bistable D flip-flop, right. Drag that in, and then chuck on a couple of inputs and a couple of LEDs for outputs. So the output that's important for us is Q. I'm connecting not Q as well, and it's traditional to leave that pin as part of what you're doing, but you often don't use the not Q unless for very particular circumstances. So immediately we switch it on and working, it's settled into one of its two states, and it's settled into the state of being high. So our data in is low, so if I click enable now, our Q should go low. If I do it again, it should be no change. If I put it to high and do the enable, it should switch. So the Q output is high. So we now have something that's actually slightly closer to resembling the idea of a memory cell, which is we have a data input which can use as a binary bit, a 0 or a 1. And then when enable is triggered, which means it's usually a pulse from a clock that goes into enable, it actively stores the state that we had in D as Q internally. And as long as the power is up and running, that and nothing else has changed at any particular point, that state will stay remembered in our D flip-flop. Right. So we will expand on this in the rest of the videos in this short series. Actually, in the next video, I'm going to show you a different version of a bistable, unlike the D, which shows a different solution to this problem of the S and the R and not being able to have them both at once. And then I'll move on from that to show you a particular use of that. But that's it from me for now.